So I want to share with you guys how I came up with my all-in-one calculus equation. Here we go. First off, I want to have the things inside of each other, and of course we have four main things, right? Of course, we start with limit, and then we have derivative, and then we have integral, and then we have series. And because I want to put them inside of each other, so I cannot have integral and derivative right next to each other because they'll just cancel each other out, so that would be super easy, right? So I was thinking, I kind of need to have the limit first, because once we get limit, we can actually end up with function. I don't want to have a limit and then I actually end up with a number, because otherwise the rest is not fun. So I want to start with the limit being inside. And the one that I have in mind is, I need to end up with a function. So of course, the definition of derivative is this, right? So this is the one that's going to be in the inside. Yeah. And next, I was thinking, should I put down series here? If I do, it's possible. But if I put down series here, then we have a trouble, because that means derivative and integrals, they will be right next to each other. So they will just cancel each other out, and that will be no fun. Of course, we can just do it like integrate it first and then do the derivative to check the answer, but not really. So either we put integral here or derivative here. And I chose to put derivative here. Of course, if you want to start with integral in here, that's okay. But you know, last time I had the derivative on the very outside, so it was not bad, it was pretty easy, right? So I want to just give myself a little bit challenge, so I put the derivative first. In fact, I will actually have the integral on the very outside. So with that being said, I really have to have a infinite series here. And then in the end, I can have the integral on the very outside. So this is kind of like the structure of my thought process. And I just have to get a good function to work with. So right here, I want to do this limit algebraically. I was thinking power functions. I think that's pretty standard, but that's pretty okay. So I was thinking to do maybe like the derivative of x to a third power, but we did that last time. So this time I try something else. I do the 1 over x squared, right? Which by the definition of derivative, I get x plus h, and then we square that, and then minus 1 over x squared, and then all divided by h. So I start with this. So of course, differentiate this by using the power rule in your head. You will end up the derivative of x negative 2, which is negative 2x to the negative 3. So this is what we have. And of course, we can totally differentiate this guy, no problem on that. And when we do that, we get 6x to the negative 4, which is this. Okay, so now I have some trouble, because we have a series of this function. What do we do with that? Wow. So I was thinking that how can we handle that situation? And I came up with the idea, of course, whenever we're talking about series, power series, we have to talk about our best friend, namely the geometry series. So I start with n equals some number to infinity. I first started with 0, and then I want to put this raised to the nth power, and that will be a geometry series, assuming that this is going to be what? The absolute value of it is less than 1, and that will converge. So that's pretty nice. Okay, so if you work that out, you will see once you do the summation of this guy. So I'll just put this down after the summation. If n starts with 0, we will get 6 over x to the 4th power to the 0th power over 1 minus 6 over x to the 4th power. The problem with this is that it's just a little bit too long, because you see this is 1. When we multiply the top and bottom by x to the 4th power, later on, I will have to integrate x to the 4th power over x to the 4th power minus 6. It's not bad, but we just have to do the long division, but I don't feel like doing long division. So instead of starting at 0, I make that equal 1. So when we do the infinite series, when we go from 1 to infinity, this right here will be 1. And then when we clean things up, you see this and that cancel. So we just have a 6 on the top right there. And then this right here, it's actually not so bad to integrate. You can just do some partial fraction business. And the trick for this is that just do partial fraction with x squared minus square root of 6 and then x squared plus square root of 6. And you will see that it works out pretty okay, I will say. And perhaps I will also tell you, this right here requires the fact that if you use the derivative of the hyperbolic cotangent, but the inverse of that, this right here, if you use this, it's going to be much easier, and that's exactly what I did in the video as well. And of course, when you integrate the sum of two squares on the bottom, that will give us the inverse tangent situation. And why this? Because remember, when we were talking about the infinite series, we have to talk about when is this going to converge. So the idea is that we have to make sure, in order for this to be true, the absolute value of the common ratio, which is the input, it has to be less than 1. And this will tell you the absolute value of x is actually bigger than 1. Like after you simplify it, it's bigger than the fourth root of 6, which is bigger than 1. That's why you have to look at this. So I think it worked out really well. Yeah. And you guys can let me know what else that we can do next time. Again, that we cannot have integral and derivative right next to each other, because otherwise that would just cancel out. I know. And I was thinking really hard, because I don't want to do the derivative, like the limit definition of derivative anymore, but I couldn't think of something else. Of course, I can always just treat x like a constant and then just maybe let t is equal to some number and compute the limit and then end up with a nice function and then do the derivative of that, and hopefully it's also nice enough, and then do the series for that. So I don't know, but anyway, I love to come up with my own question, especially because sometimes my students, they ask, why are there so many questions on the test, like if I put like 20 questions? So sometimes I would like to just condense all the concept into one question. That's why I love multiple choice questions. I love multiple choice questions because I can actually ask about like 4 or 5 questions in just one question. Of course, my students don't like this at all, but like, well, anyway, hopefully you guys all like this. And if you guys also like to come up with your own question, if you are also teaching calculus, let me know what you like to do. And hopefully you guys all like this. That's it.